Now let's try to solve a sample problem for a packed column. The problem can also be seen from McCabe 5th edition. Water containing 6 parts per million trichloroethylene or TCE is to be purified by stripping with air at 20 degrees Celsius. The product must contain less than 4.5 parts per billion TCE to meet emission standards. Calculate the minimum air rate in standard cubic meters of air per cubic meter of water, and the number of transfer units if the air rate is 1.5 times the minimum value. One parameter in designing a packed column is the tower height. In getting the tower height, one must calculate the number of transfer units, or N, and the height of each transfer unit, or H. N and H will be multiplied to obtain the tower height. In this problem, we are only asked to calculate for the number of transfer units, or N. In solving for the minimum airflow rate, we must first obtain the Henry's law coefficient for TCE. At 20 degrees Celsius, this constant is 0.0075 cubic meters atmosphere per mole. We will then convert this to the slope of the equilibrium line in mole fraction units. To convert it, we simply multiplied the constant with conversion factors. Since it is in a standard pressure, we just divide it by 180 m and then multiply it by a conversion factor of 10 to the 6 grams per meter cube and 1 mole of water per 18 grams of H2O. Then we will obtain the slope of 417. Since the slope is large, the desorption is liquid phase controlled. It is also given that the molecular weight of TCE is 131.4 grams per mole. First, we will calculate for their mole fractions. For XA, it is given that the amount of TCE is 6 ppm or 6 times 10 to the negative 6 gram of TCE per gram of water. We will multiply that by a conversion factor of 1 mole TCE per 131.4 grams of TCE and 18 grams of water per mole of water, and we will obtain an amount 8.22 times 10 to the negative 7 moles of TCE per mole of water. In solving for YA, we will multiply XA by the slope, and we will obtain 3.43 times 10 to the negative 4. Since it is stated in the problem the initial amount of TCE as well as the desired final amount, we can compute for the change in TCE, which is the TCE removed by stripping. We will divide it by 131.4 and obtain the volume of TCE removed. With this, we get 4.56 times 10 to the negative 2 moles of TCE. From the relationship of YA equals VTCE over V, where V is the total amount of gas leaving, we can solve for V. Since we already know VTCE, we just divide it by YA, which we have also solved earlier. 4.56 times 10 to the negative 2 divided by 3.43 times 10 to the negative 4 equals 132.9 moles. This is the total amount of gas leaving the system. Since 1 gram mole is equal to 0.0224 standard meter cube, and since the change in gas flow rate is very small, we can compute for the minimum air rate in standard cubic meters of air per cubic meter of water. By multiplying what we have computed earlier, 132.9 times 0.0224, we obtain 2.98 standard meter cube. Now, this is the minimum air rate in standard cubic meters of air per cubic meter of water. To calculate for the minimum air rate, we should know the density of air at standard conditions, and is given at 1.25 kilogram per meter cube. So the minimum rate on a mass basis is 2.98 standard meter cube times 1.25 kilogram per meter cube over 1000, and this is equal to 3.86 times 10 to the negative 3 kilograms of air per kilogram of water. In solving for requirement B, which is the number of transfer units if the air rate is 1.5 times the minimum value, we solve for a new value of YA. 3.43 times 10 to the negative 4 divided by 1.5, since the air rate is 1.5 times the minimum value. And then we will obtain an amount of 2.29 times 10 to the negative 4 moles. For XA star, 2.29 times 10 to the negative 4 divided by 4.17. And now we obtain 5.49 times 10 to the negative 7. We will convert XA star to parts per million or gram over gram and denote it as CA star. So 5.49 times 10 to the negative 7 times 131.4 divided by 18 is equal to 4.01 times 10 to the negative 6 gram per gram, or 4.01 parts per million. In the formula for calculating the number of transfer units, CA minus CA star equals delta CA, we obtain 6.0 ppm for CA minus 4.01 ppm for CA star, and delta CA would be equal to 1.99 ppm. For the denominator of the formula, we are given CB, which is equal to 0.0045 parts per million, or the desired amount of TCE at the product, and CB prime or CB star equals 0. Now delta CB becomes 0.0045 parts per million. For the denominator, C minus C star is equal to CA minus CA star minus CB minus CB star, or delta CA minus delta CB, divided by ln of delta CA over delta CB, or ln of CA minus CA star over CB minus CB star. By substituting the values, C minus C star equals 1.99 minus 0.0045 all over ln of 1.99 divided by 0.0045, and with this we will get a value of 0.3259 parts per million. Using concentrations in parts per million to calculate for n equals the integral of dC over C minus C star, or this is equal to CA minus CB all over C minus C star. So substituting the values obtained, 6 minus 0.0045 all over 0.3259 equals 18.4. We can say that if the air rate is 1.5 times the minimum value, then we would need 18 transfer units for our packed column. If we wish to calculate for the tower height of the column, we must first obtain the height of each transfer unit, or H. Then we will multiply H with our obtained value of 18 for the number of transfer units, and we will obtain the total height of the tower. This ends our report for the packed tower design. The next reporter is Miss Jinky Lei Kimignano, who will report on the plate tower design.